Hello again. Sorry for the delay. Okay, let's start. Okay, so let's review. Let's review very fast what we were talking about. We were talking about something called cross product. So the cross product. Okay, what was it about? Remember, we have two kinds of products. The other product we had was the dot product, right? These two products are very interesting, especially in order to study of the geometry of lines, planes, and surfaces, and things like that in two-dimensional space and three-dimensional space. Dot product actually works in any dimension. We have dot product in dimension 2, in dimension 3. That works for any dimension. But we only defined cross product for three-dimensional space. So let's just review very fast. If U is a vector, say U1, U2, U3, and if V is another vector, V1, V2, V3, the inner product or the dot product, which are the same of U and V, is equal to U1, V1 plus U2, V2 plus U3, V3. So the inner product of two vectors or dot product of two vectors is a number, just a number, right? That was the first thing we talked about. The second thing we talked about was the cross product. So again, if we have these two vectors U and V, we define U cross V to be determinant of a matrix. What was that matrix? That matrix has I, J, K in the first row, U1, U2, U3 in the first row, in the second row, and V1, V2, V3 in the third row. So we talked slightly about matrices. What is a matrix? A matrix is just, well, the first thing we can say about a matrix is that it's a box of numbers like this, 2, 3, 5, -1, 0, 2, 2, 3, 1. And the second thing we said about a matrix is that for any matrix, we can define something called determinants. Determinant of a matrix was just a number, and we had a way to compute that. So we have determinant of that matrix. There are two notations for determinant of a matrix. Either we just write determinant of that matrix, just like this, or sometimes people are lazy to write determinant. Rather than writing the determinant, they would write down the same matrix. They just, rather than, well, look at these two curved kind of lines, which they show the matrix, they just draw straight lines. That means determinant of that matrix. That's kind of, well, sometimes they write it like this. So rather than writing determinant, they just use this other notation, these two straight lines. That also means determinant. That's just another notation for the same thing. So we talked about determinant of 2 by 2 matrices. It was pretty simple. So for example, determinant of 2, 3, -1, 4. Its determinant is equal to the multiplication of these two elements, 2 times 4, minus these other two elements, -1 times 3. So it would be 8 minus 3, which is 8 plus 3, which is 11. We talked about determinant of 3 by 3 matrices. It was slightly more complicated. But we did that, and I hope you would remember. If you don't, just take a look at the book for this part. And then using determinant, we could define cross product. So the cross product of U and V was determinant of this matrix, which in the first row, it has I, J, K, In the second row, it has the components of U. And in the third row, it has the components of V. So again, just in order to review that, let's write down one example and then continue with the new subject. So for example, say if U is a vector like 1, 0, 2, and V is another vector, say -1, 4, 3. These are two vectors in three-dimensional space. We use this notation for three-dimensional space. We read it as R3. It means there are two vectors in three-dimensional space. What is the inner product of U and V? Well, it's 1 times -1 plus 0 times 4 plus 2 times 3, which is -1 plus 6 equals 5. What is cross product of U and V? Okay, the cross product is supposed to be equal to determinant of this matrix, I, J, K. Then we should write down the components of U, 1, 0, 2, and then we should write down the components of V, -1, 4, 3. Okay. Now remember, in order to compute determinant, we should choose one of the rows, this row. And then we should write plus, minus, plus here. And then we would start from the first column. Okay. Look at the remaining part, compute the determinant of the remaining part. Determinant of the remaining part is 0 times 3 minus 2 times 4. Then we should multiply the whole thing by this element in this intersection here, which is I. Okay, now let's erase this blue rectangle. Now let's look at the second column. If I remove the second column, what remains? The remaining part of this matrix is this part and this part. 1, 2, -1, 3. Let's compute determinant of this one. It would be 1 times 3 minus -1 times 2, right? Now let's multiply by this element in the intersection here, which is J. But because there's minus sign above it, we put a minus sign here. Okay, let's remove that. Now we should look at the last part. Let's remove the third column. What remains here? Its determinant is 1 times 4 minus 0 times 1. We should multiply it by K. Here we have plus above K, we should write plus. Okay. What is the result? The result is, well, 0 times 3 is 0, 2 times 4 is 8. You would get -8 times I. Here we have 1 times 3 is 3. -1 times 2 is -2. There's another minus behind it. It would be +2, would be 3 plus 2, which is 5. There's minus sign here. It would be -5J. And 1 times 4 is just 4 plus 4K. And then the way to show it as a vector is just by writing these numbers as the components. -8, -5, and 4. So it basically means the cross product of these two vectors, U and V, is equal to -8, -5, and 4. That would be the result of the cross product. Okay, that's what we learned the previous week. Is there any question here about these things? We want to continue with cross product. We want to understand cross product better. But is there any question about how we can compute cross product?
I have one question.
Yeah.
So with the plus and the minuses on top of the rows, when you're doing, like, when does that apply? When do you use that?
Well, that's in the definition of the cross product. I always would do it the same way. I mean, when I'm, that is in the definition of determinant, actually. In the definition of determinant, this is the way to compute the determinant. So it's a good question. Let me answer this question again. So when we have a 3 by 3 matrix, doesn't matter if you're computing cross product or we're just computing determinant. So if we have a 3 by 3 matrix, say 1, -2, 1, 3, 1, -2, -3, -5, -7. It's a matrix, right? When we are computing determinants, the idea is that we should use one of the rows or columns to start. I only told you how to use the first row. Actually, we can use other rows too, but just for, in order to not to make you confused, I always would use the first row. We always do that. We always write here plus, minus, plus. So the definition of determinant is this. So the determinant of this matrix would be, first look at first column, remove the first column. So if I remove the first row and first column, what remains is this part. Compute its determinant. It would be 1 times -7 minus -2 times -5. And then multiply everything by this number in intersection, which is 1, with positive sign. And then forget about this first column, look at the second column, this one. Compute the determinant of the remaining part. It would be 3 times -7 minus -2 times -3. Multiply all that by the number in the intersection, which is -2. Because here we have a minus sign above it, add another negative sign here. And then finally, we go to the last column. The determinant of this remaining part is 3 times -5 minus 1 times -3. And then we should multiply that by this number in the intersection, which is 1. And because it has positive sign above it, we write positive here. And we do all these computations and we would get the determinant. So that's the way to compute the determinant, right? That's the definition of the determinant. And even if we have, well, I don't think we are going to talk about that, but even if we have a 4 by 4 matrix, we can compute the determinant. There is nothing wrong with that. It's completely similar. If we were to compute determinant of 4 by 4 matrix, we would do the same thing. The idea is that it's alternating. So it would be plus, minus, plus, minus. And then you would erase the first row and the first column. Then you're supposed to compute determinant of this part, which you already know how to compute determinant of a 3 by 3 matrix. When you compute determinant of this 3 by 3 matrix, you should multiply it by this number in the intersection, which is 2. And then you should remove this column. And then look at the second column. Now, if I remove this column, what remains is another 3 by 3 matrix. I should compute determinant of that 3 by 3 matrix, and I should multiply it by 7, but with a negative sign, because there is a negative sign here, and I should continue that. Actually, although I don't think we are going to use this fact, but that's the way to compute determinant of any matrix. Actually, we can do that for any n by n matrix, 100 by 100. The signs here, if it was even a larger matrix, even if it was a 5 by 5 matrix, we would continue to do that. Plus, minus, plus, minus, plus. the numbers will alternate. So the sign. So they are going to always be plus, minus, plus, minus, plus, minus. Okay. Okay, let's continue to understand the cross product better. There are some properties of cross product which are quite interesting. One is that I told you the dot product of U and V is equal to the dot product of V and U. Doesn't matter which one you write first, which one you write second, right? I mean, the inner product of 1, 2, 3, this vector with another vector, say minus 1, 0, 2, is equal to 1 times minus 2 plus 2 times 0 plus 3 times 2, right? Which is minus 2 plus 0 plus 6, which is 4. Now, if I want to compute the inner product of the other way, minus 1, 0, 2 times 1, 2, 3, I would get the same thing because it would be minus 1 times 1 plus 0 times 2 plus 2 times 3, right? Which would be minus 1 plus 0. Sorry, I made a typo somewhere. Here it's minus 1. And so the result would be 5. Again, I would get 5. So the order does not matter, right? The order does not matter. However, strangely enough, that's not the case about the cross product. The cross product of U and V is not equal to cross product of V and U. And it would be interesting to understand how it would change. How can we kind of find the relationship between these two? What is the difference between these two cross products? The answer is that actually cross product of U and V is minus cross product of V and U. So for example, we just looked at one example here, right? Here we showed the cross product, in this example, we showed the cross product of U, which is 1, 0, 2, cross V minus 1, 4, 3, is equal to minus 8, minus 5, 4, right? Now, if we want to answer what is the cross product of the other way around, I would erase this line. We don't need this line anymore. I can erase these. Now, if I want to compute the cross product of the same vectors, but in the other order, if I want to see what would be the cross product of minus 1, 4, 3 times 1, 0, 2, what is that cross product? It would be negative of what we got before. So it would be minus 8 would be 8, negative 5 would be 5, and negative 4. You see, the cross product of a vector V and U and cross product of U and V in general, they are not equal. One of them is minus the other one. Okay, so that's the first property.
I have a question.
Yeah.
How did you calculate the cross product of a one-line matrix?
One-line matrix. Well, it would be
that you just did in the example.
Okay, let's see. Let me see where you're referring to here.
Yeah.
No, I didn't compute in one line. I said I erased the computation. So in this page, we computed the cross product of these two vectors by computing the determinant. I just erased it. We did it right. It was we did it carefully. It was a 3 by 3 matrix. I computed the determinant. That was the answer. I'm just writing the final answer.
Okay.
But the point I'm referring to is that if I know this thing is correct now, if I computed this thing, now if they ask me what would be the second cross product, which look, they are the same vectors, -1, 4, 3, and 1, 0, 2. Same vectors as I had before, but in the other order, right? Well, in the first case, I computed 1, 0, 2 times -1, 4, 3. Now I want to compute -1, 4, 3 times 1, 0, 2. I just changed the order. What would happen? What will happen to the answer? The answer, we should just make it, we should just multiply it by -1. Okay, so that's the idea. The third property of the cross product, which is quite interesting, is that, well, remember, if we have a vector u equals to, say, u1, u2, u3, the inner product of u with itself would be u1 times u1 plus u2 times u2 plus u3 times u3, right? Because we should write u twice and we should multiply the components. We should multiply the components and then add them, right? So it would be u1 squared plus u2 squared plus u3 squared. So for example, if u is 1, 2, 3, the inner product of u with itself is 1 times 1 plus 2 times 2 plus 3 times 3, which is 1 plus 4 plus 9, which is 14. But about cross product, something strange will happen. Actually, cross product of any vector with itself is 0. And what do I mean by 0? We should be careful. Remember, cross product of the result of cross product of any two vectors again is another vector. So when I say 0, I mean 0 as a vector in 3-dimensional space, which all of its components are equal to 0. Let's look at an example. Let's see. Let's say u is a vector 1, 2, 3. I want to compute the cross product of u by itself, right? I should compute the determinant of this 3 by 3 matrix. I, j, k. Okay. In the second row, I should write down the components of u, 1, 2, 3. In the third row, I should write down the components of u again, 1, 2, 3. And I should compute this determinant, right? Okay. I would write down the signs here, plus, minus, plus. This is the first row. I would choose the first column. I would look at the remaining part. I would compute the determinant of the remaining part. But what is the determinant of the remaining part? It's going to be 2 times 3 minus 2 times 3. And then I should multiply this thing by this element in this intersection, which is I. Okay, that should be the first column. Look at the second column. I should compute the determinant of the remaining part, which is this 1, 1, and this 3, 3 part. The determinant would be 1 times 3 minus 1 times 3 times the element in the intersection, which is j, with minus sign.
I hope so.
Sorry. Well, I didn't hear you well. If there's a question, tell me again, okay? And then I should choose the last column and compute the determinant of this remaining part, which would be 1 times 2 minus 1 times 2. And then I should multiply it by this element in this intersection, which is k. There's positive sign there with plus. But this thing, as you can see, 2 times 3 is 6, minus 2 times 3, 6, 6 minus 6 is 0. I would get 0i. Here I have 3 minus 3. 3 minus 3 is 0. It would be minus 0j. And here I would have 2 minus 2 would be 0. But minus 0 and plus 0 are the same. And finally, plus 0k. And as a vector, I should write down these numbers as components of the vector, which all of them are 0. 0, 0, 0. It's the vector 0. And if I look at the three-dimensional space, this vector, which has 0 in all of its components, is this vector, this point vector at the origin. This is a vector which is just a point. So it's a vector with no length. The length of this vector is 0. So the cross product of any vector with itself is just 0. Okay. Now there are more interesting properties of the cross product. So let's look at three-dimensional space. Say this is three-dimensional space. Let's choose 2 vectors. Say this is one vector u, this is another vector v. There are 2 directions which are orthogonal to these vectors. There are 2 directions which are orthogonal to these vectors. So if these 2 vectors are given, look at this direction. This is a direction which is orthogonal to both u and v. It makes right angle with both u and v. I'm not sure if this drawing is clear enough, but when you have 2 vectors inside the three-dimensional space, this direction is orthogonal to both of them. But there is another direction. This direction is also orthogonal to both of them. So does it make sense? So for given 2 vectors u and v, well, which they are not in the same direction or they're not parallel, there are 2 directions. Which are orthogonal to both u and v. Okay, does it make sense? Can you all visualize that? Okay, maybe it's better for me to kind of show it to you. So it's kind of important and interesting thing in both math and physics. Okay, let's say we have let's say these 2 things are 2 vectors inside three-dimensional space, right? We have these 2 vectors. Let's take another pen. These are, say, 2 vectors, okay? There is another direction which is normal to both of these directions. That's this direction, right? It's normal to both of these things. But there's another direction, which is this direction. So the vector can be the vector which is normal to both of these directions. It can be like this. It can be here. If they ask me find a direction which is normal to both of these things, it can be this direction which goes downward. It can be this direction which goes upward. So there are 2 directions which are normal to both of these. And so does it make sense? Can you all see that? And it's usually, well, it happens in math and physics a lot, which you have 2 vectors, and you're looking for a 3rd vector, which is orthogonal to these 2 vectors. And usually the way to do it is something called the right-hand rule. What does it mean? So if I have 2 vectors, I have these 2 vectors. usually people show it with their fingers, right? I have my index finger and I have my middle finger. I can use these two things to show these two vectors, right? These are these two vectors. And I want a third vector which is orthogonal to these two vectors. Actually, the thumb would be that third vector. You can do that at home. So if these two are two vectors, and then there is a third vector which is orthogonal to these two vectors, right? Now, look at the direction. I said there is another direction which is also orthogonal to these two vectors. But this direction, which goes here upward using the, I'm using my right hand. I'm not sure if Zoom would kind of flip the image or not. I don't think so. Anyway, I'm using my right hand. And the important thing is that you should use your right hand. If you use your left hand, you would get the wrong answer. You would exactly get the wrong answer. You should use your right hand. If you have two vectors, u and v, say this is u and this is v, and you want to find the direction of u cross v, this finger shows the direction of u cross v. So this is u, this is v1, which show you the direction of u cross v. So, okay, let me try to now draw it here. So if we have a vector in three-dimensional space, if we have a vector u, and if we have another vector v, if we multiply them, we would get a third vector u cross v. You might ask, where is u cross v? I'm going to tell you it's going to be normal to u and v, orthogonal to u and v. But there are two directions which are orthogonal to u and v. This is one direction. This is the other direction. Now, u and v don't need to be too orthogonal to each other. So if, okay, thank you for the question. The question is that u and v themselves, do they need to be orthogonal? No. So for example, maybe in order to kind of specify that, suppose u and v are like this, right? It still doesn't matter. I mean, I noticed that my fingers were orthogonal when I showed you my hand, but you can close your index and your middle fingers to each other, and it's still fine. And the second question as to u and v have to be in the same plane. Well, there is always a plane which passes through u and v, so they will always be in the plane, same plane. Okay, so which one is the direction of u cross v? That's the question. So if this one is u and this one, the other one is v, u cross v is always orthogonal to u and v. That's a rule. U cross v is always orthogonal to u and v. And so if the red vectors are u and v, u cross v either would be this one or it would be this one. It would be one of, it would be in one of these directions. But which one? Which one is the answer? In order to find that, your index finger should point with your right hand. You should use your right hand. So here we want to find which one is u cross v, right? What is the direction of u cross v? So the question is that what is the direction of u cross v? So when we want to find that, you should point your index fingers in direction of u and your middle fingers in direction of v, but with your right hand. Okay? And then look, where does your thumb finger point to? Which one is it? Try that and tell me. Can you do that? one person who can do that, you can, if you have camera, you can share your video and show the others how it's going to look like. I want to see one person doing this, exactly doing this with your hand to see what's going to happen. Do we have any person who's brave enough to show us where does the U cross V point to? Okay.
It should look like that.
Okay, yeah, explain. Okay, tell me. Which one is U, which one is V?
This is V, this is U.
Yeah, okay. That is correct.
So the thumb's
and then
pointing
U
down.
plus V points downward. That is exactly correct. Thank you. Yep, you got it. Yeah, that is true. Indeed, this is going to be U cross V, not the other one. And this is called the right-hand rule. Right-hand rule. Just be careful. If you use your left hand, you would end up with the other answer. And that would be the wrong answer. So here we should use our right hand in order to find U cross V. Okay. We can see that maybe in the other example too. Let's see. Okay, so if I look at the example we had here, if you look at this example, the first vector, so the order really matters. The first vector is 1, 0, 2. Where is 1, 0, 2? Well, 1 in the first axis, we have 1. On the second axis, y, we have 0. So we come here, we wouldn't move in direction of y. And the third component is 2. So we go upward by 2. We get to this point. So the first vector U is this one. Okay. What is V, the second vector? Well, it goes in the negative direction by 1, and then it goes in direction of y by 4, and then it goes up by 3. It's -1, 4, 3. If we connect origin to that point, we would get V. Now we want to find the direction of U cross V. Okay, so my index finger should point towards U. My middle finger should point towards V. You should try to do that. And then you should see, so that would be my, sorry. So that would be my index finger. And my middle finger should be like that. The thumb would kind of point towards that direction. I don't know how to really draw it, but kind of would, my thumb would be kind of like that, right? And we can't see the answer. The drawing is not really easy here. And the answer is 8. So let's say here we have 8, 5, -4. Let's see, where is the answer? The answer would be something like that, downward, which makes sense. It should be kind of downward. So it might not be, anyway, it might not be really easy very easy to see, but that's how it works. It's called the right hand rule. Let me see if I have a better picture to show you. Let me just search. Maybe there would be something better than my drawing, which makes you understand it better. Ah, yeah, there is. Of course, there is. Okay, let's let's just share this photo. Let me see if I can share a photo with you. It's good to see this one too. Okay, do you see this photo? Can you all see that?
No.
You don't have it yet?
No.
No?
Now you're showing the screen.
Oh, you have it. Okay, so
I still don't see it.
oh, you
Says
don't
you're
see
sharing
it?
screen, but I don't see anything.
Oh, okay.
Yeah, no.
Yeah, that's working. That's working.
That's good.
Okay, you see it. If there is still a person who can't see it, tell me. Okay, I would assume you can't see it now. So here you can see, here we have V cross V, right? So see that's how you should do it. The index finger points towards V. The middle finger points towards W. And they don't have to be orthogonal to each other. The angle between V and W can be anything. And the thumb is pointing towards the cross product. That's a strange kind of product. That's kind of, we are getting closer to what cross product really means. Cross product of these two vectors U and V is what the thumb of your hand would show its direction. Okay, let's go back. Okay, so we understood a few properties of the cross product, right? Okay, let's see. Okay, what we are going to do now. Okay, so okay, I think maybe I got disconnected for a second. So, okay, let's just see what we did up to this point. We have cross product. We have a way to compute it using determinants. So we know how to compute using determinants. We know cross product of U and V is not equal to cross product of V and U. Not necessarily, it's minus the other one. The cross product of U with itself is always 0. And we understood that U cross V, this cross product is always orthogonal to both U and V. So if this is U, this is V, the cross product would be orthogonal to both of them, but there are two directions orthogonal to these two. This is one direction, this is the other direction. Which one is the direction of U cross V? You learned that you should use the right-hand rule to find the direction. So in this case, let's just try that. I guess it's direction number 1. That would be the direction of U cross V. It would be upward in this case. Okay, now there are more interesting properties of cross product we like to know. The other interesting property of cross product is similar to a property of inner product. Remember, we had 2 ways of computing inner product. One was by multiplying components one by one and adding them. There was another way of computing inner product. I said it's equal to length of u times length of v, if we have two vectors, u and v. And then we should look at the angle between them. If it's theta, we should multiply it by cosine of theta, right? Now about cross product. Cross product, remember, unlike inner product, cross product, the result is a vector itself, right? So we can ask, what is length of this vector? And the answer is very similar to inner product. Actually, it is equal to length of u times length of v times sine of the angle of the angle between vectors, not cosine. So in cross product, we have sine here. In inner product, in dot product, we have cosine here. So for example, if u is, say, 1, 2, 3, and v is 0, -1, 2, find the length of the cross product, u cross v. So there are two ways to answer this question. One way is really, we can just really compute the cross product by determinants. We had I, J, K, and etc. We can compute that. And after we computed the cross product, we can compute its length. Remember, the length of something would be the square root of sum of a squared of its components. We can do that. That's one way we can do it. But there is another way. This other way says the length of u cross v is equal to length of u, length of v, times sine of the angle between them, right? So what is the length of u? The length of u is equal to square root of, this is u. The length of u would be square root of the sum of the square of its elements. 1 squared, component, sorry, plus 2 squared plus 3 squared, which is 1 plus 4 plus 9. It would be square root of 14. Okay. What about v? The norm of v would be square root of 0 squared plus -1 squared plus 2 squared. It would be 1 plus 4. It would be square root of 5. So the cross product of u and v, its length would be square root of 14 times square root of 5 times the sine of the angle between these two vectors. So if there are two vectors in R3, theta is the angle between them. But how can I find theta? How can I find the angle between them? How can I do that? Does anyone know the answer?
The u dot v, the dot product, like we did last time.
That is true. You are completely right. So remember, whenever we want to find the angle between vectors, we should use the inner or the dot product. Okay, I want you to do this now. Let's go back. Let's go to the previous page. How can I find the angle between these two vectors, u and v? I would erase this line here. It's not very important to us now. The idea was that there are two ways to compute the inner product, right? One way was multiplying components by component, the other one by multiplying the norm of u, the norm of v cosine of theta. And these two things should be equal. right? Doesn't matter which way you use, you should get to the same answer. We can use that to find theta. Okay, try to do it. I would give you 2 minutes. Try to do this. I want you to remember this thing. It's important, okay? So we have 2 vectors u and v. There are 2 ways to compute the inner product. We can use this fact to compute the angle between u and v. Do that now. Thank you. Do we have the answer? $61.44. Okay, we got 361.4, which it means it should be correct. Okay, I would do it one more time. It is important. It would be important for the exam too, so I'm going to write that again, and you also should look. There are 2 ways to compute. So whenever I ask you find the angle between 2 vectors, okay, another person got the same answer. That's good. Whenever I ask you find the angle between 2 vectors, remember there are 2 ways to compute the inner product. One is multiplying components 1 by 1. Right here we would get -1 plus 0 plus 6, which is 5. The other one is multiplying the length of u by the length of v by cosine of the angle between them. But what is length of u? The length of u is, well, we computed that. I think it was square root of 14. The length of v was square root of 5 times cosine of theta. These 2 answers should agree, which means the square root of 14 times the square root of 5 times cosine of theta should be equal to 5. It means cosine of theta should be 5 over square root of 5 over square root of 14. Okay, we should use the calculator to see what is this. Did I make a mistake? Oh, 0 minus 1, 2. Thank you. There is a typo here. 0 minus 1, 2. So here it would be 0, and here minus 1. Zero times 1, 2 times minus 1. Okay. Therefore, this thing would be equal to 6 minus 2 would be 4. Okay, here we have 4. Okay, and then we should compute the result of this to see what is cosine. Okay, what is the value? I think it's 0.47. Am I right? Is it what you got too? Okay, and then we should compute the arc cosine of this thing. So theta would be arc cosine of 0.47. Okay, so we want to know what is arc cosine of this thing, say in degrees. And it would be, yeah, it's around 61 point something. So that's the angle between them. Now, what is its sine? We want to know, remember, we wanted to compute the length of, what was the thing we were looking for? We wanted to see what is the length of the cross product. And I said, very similar to the inner product, the length of cross product is length of u times length of v times the sine of the angle between them. Now, the length of u is the square root of 14. The length of V is the square root of 5. What is sine of theta? What is sine of this 61.4? What is that equal to? Okay, we have an answer, 0.88. And then if we multiply all these things, what do we get? Someone should do that. Okay, almost, let's say 7.3. That would be almost the answer. So that's another way. That's a second way to compute the length of cross products. Let me add one more thing and we can have a very short break and we started something new. And that's another interesting theorem. If you have two vectors, u and v, using these two vectors, you can construct a parallelogram. You can make a parallelogram. How? You can, well, you can think about them as adjacent sides. You can, from here, you can continue parallel to V. From here, you can continue parallel to U. You would end up with an area with the parallelogram. And then you might wonder, what is the area here? What is the area of this parallelogram, which its adjacent sides are u and v? And the answer is the length of u cross v. That's the answer. So if you have two vectors, u and v, if you construct a parallelogram using these two vectors, the area of this thing, the area of this shaded area, this green area, the area is equal to the length of the cross product. So cross product has a lot of interesting properties, and it's another interesting property it has. Maybe it's good if I say one more thing and then give you a break, right? Let me add one more interesting thing. So we have dot product. And then we have the cross product. We can combine these two to get a new product, which is called the triple product, or triple scalar product. Now, unlike the previous types of multiplication we've seen, this product actually is multiplication of three vectors, u, v, and w. It's multiplication of three vectors. The triple product of these vectors, u and v and w, so the triple product of u, v, and w is defined to be, well, look at v and w. I can compute v times v cross w, right? That would be a new vector. That would be a new vector. And u is a vector. Look at their inner product. Look at their dot product. That is defined to be the triple product of u, v, and w. So let's compute that. Let's compute that. Let's compute one example. Let's say u is 3 minus 5, 1. V is 0, 2, minus 2. And let's say w is 3, 1, 1. What is the triple product of u, v, and w? It's inner product of u with the cross product of v and w. So when we want to compute this thing, we should start from here, actually. We should first compute the cross product of v and w. Okay, so the first step is to compute the cross product of V and W, which is the determinant of this matrix, I, J, K. The vector V is 0 to -2, and the vector W is 3, 1, 1. Okay, I would write, this time I would write slightly faster because we've done it a few times. 2 minus 2 would be +2 times I, minus something times J. It would be 0 minus 2 times 3 would be +6, plus something times K would be 0 times 1 minus 2 times 6. So it would be equal to 4I minus 6J minus 6K. That would be the cross product of these two vectors, which if I write it in the form of a vector, it would be 4 minus 6 minus 6, right? Now, the second step is to compute the inner product with U, right? Compute the inner product with the vector U. But vector U is 3 minus 5 and 1. And here the result is 4 minus 6 minus 6. The inner product would be 3 times 4 plus minus 5 times minus 6 plus 1 times minus 6, which is minus 6. Would be 12 plus 13 minus 6. It would be 36. 36 is the triple product of these three vectors. That's the way to compute the triple product. There is a second way to compute the triple product. So, second way.
Can you go back for a second? Sorry, I wasn't finished writing it down.
Yeah, sure.
Thank you. You can go to the next one. Thank you.
Yeah. So there's a second way to compute the triple product. Rather than computing the cross product first and computing inner product with U, we can do all of them at the same time. We can write down these vectors here. So what was U? U was 3 minus 5, 1. V was 0 to minus 2, and W was 3, 1, 1. We can just write them down in a matrix. 3 minus 5, 1, 0 to minus 2, 3, 1, 1. This is a matrix, right? Actually, the triple product of these three is equal to the determinant of this matrix. We can just compute the determinants directly. So plus, minus, plus. So this is first row. We can take the first column. The determinant here would be 2 times 1 minus 2 times 1 times here 3. And then the second one would be minus. Determinant would be 0 times 1 minus 3 times minus 2. We would multiply it by minus 5. There is another minus sign there. And finally, we would look at the last column. Finally, we would have 0 times 1 minus 2 times 3, and we would multiply those by 1. And there's plus. If we do this thing, it would be 2 minus 2 would be 4. 4 times 3 would be 12. It's 0 minus 3 times minus 2 would be plus 6. And then we should multiply it by minus 5, would be minus 30. There's another minus here, would be plus 30. And if you look at the last one here, we have 0 minus 6 times 1 would be just minus 6. If we do the computation, you would get 36 again. So there are two ways to do the triple product are basically the same. We can either do the cross product first and then do the inner product, or we can directly write all of them in a matrix and compute the determinants just directly and get to triple product. And why are we interested with this kind of product? Well, the last thing I'm going to say, it's really the last thing. If we have three vectors, u, v, and w, let's say this is u, this is v, this is w, right? We can construct a parallel pipe with these things. If I continue from here, parallel to the other sides, and continue from here parallel to the other sides, we get something like this. You might wonder, what is the volume of this thing here? What is the volume of this thing here? When the sides are u, v, and w. The volume is equal to triple product of u, v, and w, which is u dot v cross w. So the volume of this thing is equal to triple product of u, v, and w. And we can compute that by just the way we saw. We can write down u, v, and w in a matrix and just compute the triple product. So for example, and this is something interesting. Well, it would be hard for you to compute that if we didn't have this theorem. So for example, if they say u is 3, minus 5, 1, v is 0, 2, minus 2, and w is 3, 1, 1, we would have three vectors here, for example. Look at the parallel pipes constructed by u, v, and w. It would be something, well, it's hard to draw a little. It would be something like this. If they ask us find the volume of that, we would say it would be u dot v cross w, which is determinant of 3, minus 5, 1, 0, 2, minus 2, 3, 1, 1. And we did it. It was 36. I should say something. It's a good question someone asked here. If we change the order of u, v, and w, the answer might become negative. So if I change the order here, for example, if I write v times u cross w, or any other thing, if I change the order of these three things, only the sign here might change. It might become, for example, minus 36 or something like that. But remember, volume, well, at least here in this course for us, is a positive number. So even if you get minus 36 here, you should say the volume is the absolute value of that. Even if you end up here with minus 36, you should report the positive value of that number. You should say the volume is 36, at least in this course, okay? So for us, the order does not matter much. Actually, what will change is just the sign. Okay, that's for this inner product and cross product. We finished that. There are a lot of things here, and it's quite interesting. You should read the notes more carefully, and you should solve exercises here to understand it better. And then if you have any question, you should ask me. Okay, let's continue at 10:30. Let's have a kind of 10-minute break. Is that good?